Hi everyone, we are back and now we're going to get into describing some of our critical crystalline structures, and we're going to start with something simple cubic. So once we're in 3D, we're going to describe basically our lattice, which again is going to expand into infinity through 3 lattice constants, 3 interaxial angles, and for a simple cubic, it's very straightforward. It's basically 90-degree angles for all those interaxial angles, and then all of our 3 lattice constants will have the same length. So let's take a look at the structure. So for simple cubic, we have atoms at the corners. So we usually draw the structure like this, but in reality, the atoms are touching here. So the atoms here are overlapping and touching. Thus, we can describe this lattice constant, this lattice parameter A, is equal to 2 times the radius of our particles. And again, we're assuming a pure material, so we're going to assume they all have the same radii. So spheres of equal radii. So how many atoms are in our simple cubic unit cell? Well, it looks like we have 8 atoms in the corners, but remember, I have a unit cell right next to it here. I have a unit cell behind it here. I have a unit cell coming out of the board here. I have a unit cell coming out of the screen here. And then I have basically cells on the bottom the same way, and then cells on the top. So if you look at this atom is shared by 8 other different cubes or cells. So an eighth, 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 an eighth. So our simple cubic unit cell has 1 atom. Our nearest neighbor distance in this atom, or in this structure, is going to be this distance here, this A, 2r. Nearest neighbor distance is always going to be equal to 2r. What's our next nearest neighbor distance? The next nearest neighbor distance will be this diagonal here. So that next nearest neighbor distance is just going to be 2r root 2. That's just some geometry right there. What are our number of nearest neighbors? So if I look at this atom, this is a nearest neighbor, this is a nearest neighbor, this is a nearest neighbor here. But remember, that's 1, 2, 3. But there's going to be one that's going to come out of the board here. There's going to be one out of the board here. There's going to be one at the top as well. So if I look at it, basically 1, 2, 3, 4. Sorry here. 1, 2, 3, 4, 5, 6. So we should have 6 basically nearest neighbors. Forget about the next nearest neighbors. What is the atomic packing factor of this cell? So atomic packing factor is incredibly important. So the atomic packing factor is just a ratio of the volume of atoms over the volume of cell. And if we have an atomic packing factor value of 0.74, which is the maximum theoretical, the most dense structure that you can create, that you could pack equal size spheres in a cube, that is our kind of geometrical limit, that 0.74 value. So we can't go higher than that. So volume of an atom. So for a simple cubic, how many atoms do I have? So I have 1 atom. What's my volume of the atom? 4/3 pi r cubed. What's the volume of my cell? A cubed, and I know A is equal to 2r. And this is where we're going to pull out our hand. So let's call A of simple cubic is equal to 2 times r. And then I'm going to do basically 4/3 times pi times r cubed. And we're going to divide all of this by ASC cubed. And then let's look at this numerically. And don't hit the value. So this is not a close packed structure. So if it's not a close packed structure, that is going to have some severe implications on the mechanical properties, and we'll see that as we kind of move forward. Excellent. So let's go ahead. We've already calculated that. What about BCC? Body-centered cubic. So BCC looks like this. So same as simple cubic, except now we have an additional atom at the center here. If you look at a BCC structure, you'll see that the nearest neighbor distance is actually this distance right here. So, and actually, taking one step back, when we look at what are our close packed distances or close packed directions in this structure, you can see that it's this direction here, this direction here, this direction here. So our 1, 0, 0 direction is our close packed directions here. So I can have close packed directions even though this cell is not officially close packed because of atomic packing factor, and we're going to see soon that there actually are no close packed planes in this structure as well because we're not close packed. So I can have close packed directions in a structure that's not close packed, but I can't have close packed planes. I can't have close packed planes in a structure that is not close packed. But anyways, so these two atoms are touching, and these atoms are touching here. So that distance here is this 4r. So if I'm trying to find my A, this distance here is 4r. I know that this distance is A, this distance is A, and this distance here is A square root of 2. So I can solve for A. My lattice parameter is going to be equal to 4r over square root of 3. Again, you can prove that geometrically. You can see that here. But anyways, so you're seeing that the cell is actually, this is greater than 2r, which is what we had previously. Our nearest neighbor distance is still 2r, atoms touching, but our lattice parameter A has gotten larger. What about our number of cells, or number of atoms, excuse me, in our cell? Well, we could actually look this up and calculate it. So I still have an eighth, an eighth, an eighth, an eighth, an eighth. So I still have one from the corners, and I have a central atom here. That's only shared by itself. So there are 2 atoms in this unit cell. What about nearest neighbors? Well, I've got a nearest neighbor 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 nearest neighbors in my BCC structure. Second nearest neighbor distance. What about atomic packing factor? So let's do the calculation again. So how many atoms do I have? 2 times 4/3 pi r cubed divided by 8 cubed. Except now our ABCC is equal to 4 times r divided by square root of 3. I'm going to grab this over here, copy and paste. I'm going to do a 2 in front of it because there's 2 atoms. ABCC. Still not close packed, so it is not a close packed structure. What would be my close packed direction in this plane? So this direction here, or this direction here, that's always going through atoms. There's never space. If I go through here, there's empty space here. So my close packed directions are our family is going to be my 1, 1, 1 direction. Additionally, again, can't emphasize this enough, there's not going to be any close packed planes in the system because this is not a close packed structure. Face-centered cubic. This is always kind of the nastier one to draw. So now, always have my atoms at the corners, but now I have an atom at the center of each of the 6 faces of my cube. So, again, here, if I look at this atom, this is these atoms here are touching. So this is 4r. This is 4r, this is A, this is A. So now, again, nearest neighbor distance is still 2r, but my A now has grown to 2r root 2. So this is even greater than the BCC structure. So actually I'm going to go ahead and I'll plug that in later. So you can also see that my number, so what are the number of atoms? So still have a half here, or actually, excuse me, an eighth from each of those, that contributes 1. But if I look at these atoms on the faces, they're only sharing 2 unit cells. So for example, this one would be the one right next to it right here. This atom is shared by this unit cell and this unit cell. So it's only half. So my total number of atoms is going to be 4 in this unit cell. So, excellent. So I've got my number of nearest neighbors. Again, you could kind of look and start to see at this point now that you'll see it's 12. And now, second nearest neighbor distance. What about my close packed directions? I see these directions will work, so I get the 1, 1, 0 direction will be my close packed directions. Is this a close packed plane? Let's figure it out. We know the formula at this point. I'm going to copy this, put it down here. A FCC is equal to 2 times r times square root. Not square root of 3, square root of 2. Glad I caught that. That would have been a long time. Oops. And then again, 0.74. So that is indeed, we've got Yahtzee, everyone. So that is indeed a close packed, that's a close packed structure. So there will be indeed a close packed plane in here, and we'll get to that in the next part. So this atomic vacuum factor and these close packed structures is going to have huge implications. Usually materials that are close packed, FCC, HCP, they are going to be more ductile as opposed to BCC or simple cubic structures, which are going to be more brittle. And that is indeed a problem once we get into trying to look at and designing materials and putting them in mechanical applications. So that's it for this time. So we'll see you in the next video when we looked at close packed directions, which we've already covered, and then close packed planes and calculating planar density. So see you in the next one. Thanks. Bye.